All right, so I want to talk about energy methods in universal gravitation problems. And you probably already know the basics, but let's do a quick review. All right, so just kind of big picture. Typically, but not always, if we want or are given acceleration, we typically do a force problem. Not always, but usually. That's Joe. Let me do this button here. Oh, where did it go? Did I let you in? Sorry about that. This is kind of a theme from the whole semester. It's not always true, but typically if we want or if the problem gives us acceleration, we usually think force. Not always, but usually. There was kinematics as an obvious exception, right? If we want or are given V, we typically do an energy problem. Probably the most notable exception on that one is if you have constant speed, not velocity, speed, in a circle, we oftentimes did an FBD, right? You know what I'm saying? So this is just kind of big picture stuff, right? And so the same holds true with energy methods. And I want to emphasize something else here. A lot of you have some experience now, and you know constant acceleration kinematics are really useful if we can use it. There were some exceptions, right? If you have a swinging pendulum, alpha was not a constant. Remember that? As a pendulum swings, the torque changes, so the alpha changes. Let me give you another example. Let's say you had two point masses. Let's say we have object 1 and object 2. As they move, let's say they're released from rest, there's going to be a force of 2 on 1. Oh, whoops. 1 on 2. This is on 2. Do you agree? That should be on 2. 1 on 2. This one was force of 2 on 1. As they move, they attract each other with universal gravitation. As they move, does the force change? Yeah. Forces change as they move. So if the forces change, does the acceleration change, or is it constant? It's not constant. Agreed? So maybe I'll put these right here in their own box, just so it's clear what I'm talking about here. We want to be careful trying to use kinematics. So what I'm trying to do is give us some insight into why we might want to use energy methods. We know that if we have acceleration, we're typically going to do a force problem. If you're doing a coding problem, this is pretty easy to handle, right? We could just split it up into small time steps so that A is approximately constant for each time step. But then what about situations where they're going to move large distances and we want to get a paper and pencil result to check our code? Right? We might want to do an energy problem and figure out the final speed of an object as it's moving around under the influence of gravity. Cool? All right. So the big picture of this, the general strategy, you draw a before or an initial state, and you have a final picture, right? Maybe there's three masses here, right? And maybe they start coming together. Maybe in the final state, they're all moving. Okay? And what you could do is you could write K initial plus U initial plus K final plus U final, right? Now, typically, we ignore this term. Why do you think the work external and non-conservative goes to zero? Gravity is going to do work on these objects. Gravity is going to speed them up. Why do we ignore the work done by gravity?
That's what we're looking for.
Because
that's what we're dealing with, because that's the whole reason why they're moving towards each other.
That's
So
right.
it's not outside force.
Yeah.
Inside that point.
Okay. Also, what do we know about gravity and energy? Does it conserve energy or not? Gravity is a conservative force, so we are going to account for it just like you said, and we're going to account for it in our U's instead of in our W's. So it's not like gravity doesn't do work. It's that gravity appears here. There's going to be work done by gravity, but we're going to account for it as potential energy because gravity is a conservative force. Good. And typically, these problems happen in outer space. How does that help out? No drag in outer space. How about we say negligible drag, okay? So that's the assumption we're going to make for these types of problems. All right? Obviously, if you had a comet that was coming towards the Earth and it starts entering the atmosphere, that would be more complicated. We couldn't do this. We'd have to account for that somehow. All right. Does anybody remember the equation for UG from last time? For big G? Instead of MGH, we used negative something. What was it?
GMM.
Got it. And it was R to the first power, not R squared. The force has the squared in it. So at this point, it's pretty straightforward. Do you agree? We just plug it. And so that's what's kind of cool about this. We kind of beat you up in chapter 8, trying to get this technique to be automatic. And throughout the rest of your physics career, what do? Well, we just say, hey, by the way, there's a new type of conservative force. We can account for that energy this way and just plug and plug and plug and just keep going until we're blue in the face. All right, so let's try 13.9. I'm going to erase the board over here in a sec. So take a look at 13.9. That's the background. You might be able to solve it without me lecturing anymore. If you want to race ahead, go for it. All right. (13.9) Escape from the planet of the physicists. We're going to start out with a set of pictures. Initial, the planet here with some radius r, some mass big M, I think. Yep. And then a bunch of non-physicists who just can't take it anymore and they've got to escape. They're going to launch from this planet with some initial speed v, and then in the final state, there's still going to be a planet there. These people are going to be hella far away. And if they just barely escape, you got to know this, people. You got to know this fact if this problem shows up, okay? Which this is one of the problems I really like. You got to know this. What's the minimum speed you would need really far away to say you've escaped? Like 1 mile an hour, right? Or 0.1 miles an hour, or 1 meter per second, right? You have to be just barely moving. Once you're far away. And so to be clear, that's what it means to a physicist to escape. You may not get anywhere, but effectively you get really far away and you're just barely moving. Well, approximately what's a good value of velocity for just barely moving? .1 meters per second would work. 0.01 meters per second would work. 0.001, what's a good number? 0. So if we round this off to 0, that would be the speed you would need to go to escape. Obviously, it can't be exactly 0, but it could be just ever so slightly above. Is everybody cool with that? So if you get a problem like this on a test, you're supposed to know to escape means you get far away, but you're not moving anymore. Any speed greater than that, you would also escape. But this is the minimum conditions to escape. Good? All right, all right. So now, let's write down. I'm going to set the work term to 0. Obviously, this is not perfectly accurate because to escape the atmosphere of the planet, there would be some work done, but we're going to ignore that. Maybe we got to start somewhere. So maybe I'll make that comment. Obviously, the planet has some atmosphere, but we're going to ignore any of those drag forces. Those are not truly negligible, but we got to start somewhere. What's the initial, I don't know, what's the initial kinetic energy? What should I write for that? Oh, by the way, this has mass m. Doesn't it, little m?
It doesn't really say.
I didn't say it, but
All right. Let's assume it has mass little m. If it doesn't say it, what do you bet it drops out, right? So let's give it a mass. Okay, so what's the kinetic energy initial? Don't overthink it. What's the equation for kinetic energy? And do you agree in the initial state we have mass little m and speed little v? So let's just rock it. Is everybody okay with that? What's the initial potential energy? What's the equation for it? Just tell me the equation. Negative. What? Yeah. What's the distance between them in the initial state? Approximately. Capital R. Do you agree? It has to be the center to center distance. It's not this distance that matters. This is the center to center distance. Do you agree? For most spaceships and things like that, even if they're 100 meters tall, that's negligible to 4,000 miles, right? So you might be saying, does the size of this matter? Not usually compared to the size of a planet. So here, is it R or is it R squared? It's just R. The energy is just R. Okay, got it. Now, in the final state, what's the kinetic energy? What's the radius approximately? What's a good name for that radius? If you're really far away, it's approximately infinity. Okay? You could say it's 10 to the 9th meters. You could say it's 10 to the 6 billion meters, right? 10 to the 6 billion would be a really big number. Well, let's just see what happens here. Oh, whoops. I was doing the potential, my bad. What's the final kinetic? I'm sorry, I screwed up. What's the final kinetic when you're at this far away radius? Approximately, yeah. And notice, if your speed is close to 0, then you square it, it gets even closer to 0. So it's really, really negligible. Now we got this minus G, big G, and I'm going to cheat and shove in the approximate radius. What is this term approximately equal to? Well, to 1 over infinity, approximately. What is it?
0.
Yeah. Cool. Remember what I was saying last time? When you get far away from something, gravitationally speaking, we say you've escaped when you get to 0 energy. When you're close to the planet, you're going to have negative energy because this term is going to dominate, right? Well, if you're able to escape, the initial kinetic energy is able to offset this, and you're able to get far away from the planet. So anytime this term is bigger than that term, you can escape. Anytime this term is bigger than that term, the planet keeps pulling you back in. Got it? All right. So in this case, let's just work this out. Oh, what conveniently drops out? So it turns out the satellite mass doesn't matter. It's the planet that determines the escape velocity. The bigger your planet, the more velocity you need to escape. All right, let's write this out. Notice that minus sign is critical, right? Because it allows us to bring that to the other side. And I think last time in lecture, I may have misspoken a little bit when we were talking about circular orbits. This is the velocity you could set to C and get a black hole. Think about it. You need this much speed to escape the planet. So that's your escape velocity. We'll put escape down here. I should say carefully, that's actually escape speed, right? There's no vector on it. So in this case, if you plugged in the speed of light for this term, that would give you the size of the mass to radius ratio for making a black hole. Now think about this, mass to radius ratio, that's effectively somehow related to the density as well, agreed? So mass over 4/3 pi r cubed for a sphere would give you a density. So this kind of, you could rewrite this in terms of density and radius or something like that. But yeah, anyways, cool with that? Now I have a simulation that I thought I might show you. And while I'm getting the simulation ready, I want you to think about this. It's going to take me a minute to load this up. Here's my question. Which way do you need to point the mass to escape? Or is it a range of values? That's the question. You understand it? If I want to escape, do I have to point straight out or can I go straight up or which way? You think about that while I get the simulation ready. Okay. Oops. And you can talk to your neighbor. You can read the rest of the problem. See if there's anything else you want to cover in there. Where is that one? This up. Thanks for your patience. Wish I would have thought of that when we were building this, to put all the switches right in the middle of the classroom, right? Oh, well. Not what we got. Share screen here. It's starting to come up. There it is. Okay, so hopefully you can see this on my screen. Should I turn off more of the lights just so it's a little darker? Sorry. The screen is kind of fake all the time. Is that better?
Yeah.
All right, so to be clear here, I haven't clicked to start the simulation yet. It's supposed to be a simulation of what we were just working on. Notice they're just barely separated. And when I click, let's see what happens here. It goes flying way out. And it's coming back, right? So it did not escape. So the idea is in this code here, oh my gosh, come on. We've got our standard constants, coordinate systems, etc. And we can come in here and we can change the initial parameter. So what I'm going to do now, let me run this program one more time. This time I'm going to run it with auto zoom out. And I want you to watch something. It's zooming out, it's getting farther and farther away, but it gets pulled back in. Now, if I scroll down, you can see what looks like the center to center distance over time. It's getting farther away, farther away. In this particular set of numbers that I used, it got about 175 meters away. What if we go again? And let's try 595. It should get closer to escaping. I think I ran this the other day. So let's run this. It's getting much farther away, but it's still not quite enough. It's going to get pulled back. Oh my gosh, look at this. Right, so look at the distance. It is slowly creeping up, but you can see it's starting to curve back down. Do you see that? And there it goes. So if we go back up, now it's going to, do you see it starting to creep backwards?
Yeah.
All right, sorry, I should have upped the simulation time on this one. Oh my gosh. Are we getting close yet? Okay, it's starting to come back. Zoom in a little bit so you can see better. Sorry. They're not playing that very well. I should have upped the simulation speed, right?
Yeah.
Oh my gosh. Is this thing ever going to finish? We know it's going to start picking up speed. But notice the acceleration is not constant here, right? When it's way out there, now it should start speeding up dramatically. And I think I'm hitting the limits of the simulation speed here. It's getting a little blocky. Sorry about that. All right. So just to make this clear, let's up the simulation speed to 1,000. Right? And now let's put this up to say 598. Oh, 597. When I run it this time, it's going to go away. And when we look down here at the graph, at this point, you pass a certain level. Sorry, that's beeping here. Notice it's not flattening out anymore. It's just becoming a straight line because the velocity is constant. So at this point, it's able to escape forever, and we could just keep running this code and it would never come back. Let's go to the question we had. So that's pretty fun. Now my question to you is this. What if I make this 0 and I make this 597? What should happen? Will it still escape? What do you think? Was there anything in the problem that suggests the direction matters? When we did an energy, no. So when we do it this way, obviously it mattered, right? We see that there's this complicated thing right at the beginning, but it still escapes, right? And so by that token, what if I set this under? Let's do 590. When I run it like this, what should happen? We get an orbit. Now keep in mind, this was just barely spaced above the surface. Do you remember that?
Yeah, when I tried to do it, it just kept colliding with the.
Yeah, so check out what I did in the code here. Look what I did here for the position. What I did is I put it 1% above the surface.
Okay.
And so, but, right, and we can even make that even smaller, but basically, if you don't have enough velocity to escape, you're trapped, right? If the gravitational energy is a larger negative number than the 1/2 mv squared, you get stuck in orbit because your total energy is negative. If your total energy is 0, you just barely escape. If your total energy is greater than 0, positive, your kinetic is greater than the gravitational and you can escape. Is that enough on that? Sorry if I was a little slow getting through that. I just don't know any better way to do that than to show a simulation. Any questions while we've got it up? So if you didn't get this done last week in lab, you could figure this out this time. And yeah, it's basically the same crap, but yeah, you just, all right, that's enough. I think that's
It's on YouTube now.
yeah, exactly. You can look it up. All right. So where is that? What were we doing? Oops, I don't want to end that. Let's sorry, I always get confused coming out of a screen share what I'm supposed to be doing. It's weird when I'm lecturing like that. So let me get the lights back on and get the screens on. All right.
And don't account for the kinetic energy of the past separately.
Exactly. I'm ignoring the kinetic energy of the planet. Obviously, its mass is huge, but that means its velocity is small, and since it's v squared, that term usually ends up being negligible. To be fair, we could do the same problem a different way. So since you asked, cool that you are, let's see what would be different. And this is good because this is like related to test questions, so it's not like it's a bad idea to talk about. Let's say we did the same problem. Okay, so I'm just making one up. Okay, made up problem. This is not in the book right away. There's probably similar ones in there, but I'll just make one up. Let's say we have two masses, 2m and m, right? And in this case, let's say they're each initially moving apart with the same speed v. So here's a case. Do you agree if the masses are comparable, they might both be moving? All right. So for some reason in this particular problem, let's just say somehow there was a spring in between them or whatever, or a rocket thruster that gave them an initial speed, and they both happen to have the same speed for this case. I could mix this up on test day by saying this is 2v and this is v over 2 or something, or m and 6m or something, right? Whatever. Just plug in some letters there. But in general, let's say this is the initial state. And in the final state, and actually, you know what I'm going to do by symmetry? I'm going to make this one v over 2. Because I don't want to have to explain something, okay? So the bigger one, let's say you put an explosive in there. Hopefully you agree that the lighter one would have twice the acceleration and end up with twice the speed. So this is a more realistic problem, right? If we put an explosive in there and blew them apart, the bigger mass would have, that way momentum was conserved. You know what I'm saying? Again, I'm assuming, let's say you had a mass here, 3m, put an explosive in it and it blew up. And as a result, these flew out. And now that's where I came up with these numbers. Everybody good?
Yeah.
I like this one more. Sorry, this is what happens when you make a problem up on the fly. You got to think. All right. So in the final state, they're going to get really far apart. and their speeds should slow down. And hopefully they stop somewhere way out there, or basically come to a crawl. Now let's think about this. Which one of these objects is going to have a larger gravitational force on it? M or 2M? Which one has more force acting on it? Same by Newton's third law. I tried to trick you. Does that make sense? Right? Do you agree it's G, M1, M2? Well, they're the same masses over the same distance. The force is the same. The magnitude. Now, obviously, the force direction is opposite. Now think, which acceleration should be bigger? Which acceleration should be bigger?
Oh, small.
The smaller one. Do you agree A for mass M should equal twice A for mass 2M? They have the same force. If you divide force by mass versus force by 2 mass, right? This one should have half the acceleration. That's why it's okay that they both go to 0, right? This one started off with half the speed, but it also has half the acceleration. It makes sense that it'll fall off in this way. Is everybody following that okay? So now in this case, what's the initial kinetic energy? Start giving me some formula. Don't try to do it all in your head. What's the formula for kinetic energy?
1/2.
Yeah, and then we got 2 terms, right? So let's just do it one at a time. I got 1/2, I've got a 2m, and then I've got a v over 2 quantity squared. Because if I try to do all this in my head, I'm going to screw up the 2's. Then I also have a 1/2 m with just a regular v squared, right? What's the initial gravitational potential energy? Well, what's the thing I always harass you about first? Negative. Big G. There's going to be m. There's going to be 2m. And then what's the distance between their centers? In code, we've always been saying it's like rock 1 dot radius plus rock 2 dot radius. You know what I'm saying? However, can we just cheat and call it, how about 2 times the radius? Let's assume they're approximately the same radius. I'm going to assume the masses have the same radius, big R. Okay. So then down here, that becomes a 2R. Is this kind of where you were wanting to go?
Yeah.
Like how you would approach it? Big picture. I mean, let's be real here. You guys are going to go on and do much cooler stuff in your life than what I'm doing, right? So this problem is actually kind of a good view behind the hood of what should be going on in your brain when you're first assigned a problem as an engineer or a scientist. I'm stumbling around, thinking it through on the fly, and then I'm listing what assumptions I have to make so that the problem is doable. And then if I need more detail, I can come back later and say, what if they were different radii? What if? But you document just a set of situation and just start somewhere and get something done, and then you can improve upon it and improve upon it. As engineers, we call that prototyping, right? You make a prototype, it fails. You're like, oh, it failed because of this. You make another prototype, it kind of works, but it's really crappy. So then you make another prototype and you just get better and better. Same thing with theoretical physics models. Start with the easiest one that's solvable and improve upon it until you get to the right level of complexity that handles your real life situation. Sorry, I'll get off my soapbox. What's the final kinetic energy? Approximately 0. What's the final gravitational energy in this state? What did we assume if these things were escaping each other? Because remember, we're trying to do an escape problem. What do we typically assume about the final radius? Yeah. Right? So they have to have 0 velocity when they're far apart. So we, whoops, not 0. Sorry about that. So what is U final equal to?
0.
Yeah, that's the one that's approximately 0. And there you can do the same work again. Agreed? So that would give you an idea of what size explosive charge you would need to use so that these asteroids could separate. Like say you want to put a nuclear bomb in here, how much explosive power do you need so that the asteroid actually escapes itself and separates? Cool? What do you think? All right. Oh my goodness. Let's take a look at, oh my gosh, I'm so passionate about 13.12. I want to do it. Let's come back to 13.11 and 13.12 at the end of class if we have time. Okay. Before we do that, I want to mention something. Let's go into here. If you plug in numerical values, we didn't do that. Let's plug in and get a numerical value for the escape speed really quick. So I'm going to go back to the other board. Get our calculator on today. Just finishing up 13.9 before we go below and past it. Okay, so we're going to use the parameters for Earth. Again, this will be Earth without an atmosphere, so it's not exact. But 2 times 6.67 EE negative 11 times what was the mass? 5.97. What was it? EE 24? 24. And then divide by 6370 kilometers. So 6370 EE3. Then I'm going to square root that. I got 11.2 kilometers per second, approximately. All right, 11,000 is 11 kilometers per second. Now think about that. Did you end up looking up the AK? Was that the right muzzle velocity? Yeah. And you know, it probably depends on the ammunition used and things like this. I don't know enough to say this, but right. So if you shoot an AK-47 up in the air, the bullet's not going to escape. So it's going to come back and it could kill somebody. So I know when the semester's done, you wanted to go out and just party. Maybe maybe don't. Maybe don't shoot off your AK all the time straight up in the air. All right. That's my tip for today. Oh, part D is kind of a fun one. We discussed this a little bit already. The United States has a huge advantage in launching spaceships over Russia, right? The advantage is we're closer to the equator. Florida is pretty close to the equator, relatively speaking. Why is that advantageous compared to being in northern Siberia? Ooh, since we got a globe.
Less fuel.
Why?
We have a greater initial velocity.
Exactly. Remember, the direction doesn't matter. If you're now I got to pull these sticks out real quick. Oh, let's put it right there, right here. So if you're spinning, and if I could, oh my gosh, it's kind of hard for me, but
Should someone grab it and then you can?
it's fine. Oops. I'll just start spinning it. We get the idea here. The idea is if you're sitting right on the equator here, you can see that there's more kinetic energy near the equator than there is up here near the pole, right? So up near the pole, you have a smaller radius from the axis, so your velocity equals r omega is close to 0, right? The velocity on the pole is close to 0 versus on the equator. So if you're spinning, that gives you more kinetic energy. When you launch, it's easier to get into space because you need less fuel, you got less weight, and so it just gets a lot easier to launch things into space from Florida. Cool? So what good is Lompoc?
Well, it's an information center for my project.
Yeah, but it also has advantages as well in terms of launching. Now, to be fair, I'm not an expert, but what I've heard from my students that have parents that work in the launches on base, they say, we're never getting rid of Lompoc. Polar satellites. So evidently it has something to do with launching satellites into polar orbits, right? And I don't know, but I wonder if it has something to do with the direction you have to launch it and being able to launch over the ocean so that you're not going to have giant explosions over large population centers if they fail. But I don't know. So go look it up and find out why Lompoc is used for polar orbits. Okay, that's the. Ooh, I love starting a rumor. Oh, cool. All right, it'll be there forever. All right. Anyways, that's kind of interesting. Good. Yes.
So when a rocket launches, like in that case, like just like outwards, it's gonna travel outwards, right? But to us, it seems like it curves.
Yes. Yes. Remember in the escape velocity, right? Unless you're perfectly radial away and account for the rotation of the Earth at your latitude, right? As you launch, we're going to see it rotating relative to us because we're on a curved surface that's rotating. So yeah, it's complicated. Is that good?
Yeah.
Yeah, yeah. And when you launch it, right, it's got the component upwards plus the component from r omega of the Earth's rotation. So the total velocity would be velocity of the spaceship relative to the Earth plus velocity of the Earth relative to whatever object you care about, Mars or the sun or center of the Milky Way or whatever. Yeah, so it's complicated in that manner. Is that good enough?
Yeah.
Yeah.
I was gonna say, if it's so beneficial to launch from the equator, why doesn't the United States pair up more often with Europe? Since France owns French Guiana and they even have a launch method.
I don't know. I mean, yeah, that's getting into politics. I really don't get that, man. Right? Yeah, it's like, why don't we feed all the children on Earth and give people fresh water to drink? We don't do that either, right? Instead, yeah. So don't get me started on that, man. I don't understand this planet, but not ready to escape yet. I'm only at like 1 kilometer per hour. Anyways, yeah. All right. Other questions? It's a good one. I just don't know. Yeah, and maybe they do this, and maybe we just don't know. Maybe they're launching from Ecuador. I don't know. Yeah. Okay. Yeah, good stuff, right? Something else I wanted to mention. Elliptical orbits. If we wanted to model elliptical orbits, what's the best technique? Let's say you wanted to study elliptical orbits. Have you seen any techniques that we've already used in class today? Starts with C. I'm singing a song that's a tribute to someone. It's an ode. What's that? Code. Sorry, that was like the worst hint towards code. Why would we do anything other than code it, right? Elliptical orbits, the math is extremely complicated. If you really wanted to see the paper and pencil math involved, 13.10 shows you the paper and pencil math for figuring out elliptical orbits. I recommend never doing that problem, learning how to code instead. But the trick is you can do conservation of angular momentum. So I will mention it this way. Let me go way over here before I erase. If you have an elliptical orbit, right? Let's say you have an elliptical orbit like this. I don't want to spend too much time on this. But at some random spot in the orbit, I just want to point out there's going to be a gravitational force towards the center. Well, if I know about angular momentum, L is R cross P. Do you remember that was one of our first problems we did in angular momentum? We talked about angular momentum. You can do a radius vector cross its P. And now notice, in this case, we're going to have a gravitational force here. There's a force due to gravity. How much torque is there about this pivot? If I choose this as the pivot point, what's the torque due to that large gravitational force about this pivot point? What's the torque?
Are you on the screen?
Yeah, I think so. Right, Jules? Yeah, thanks. I checked. Thanks for checking though, Michael. I appreciate it. Yeah, I went off preset. Why is the torque 0 for this gravitational force? What's the phrasing I want you to use? Line of action through the pivot. Do you agree, no matter where it is in the orbit, the gravitational force is pointing right towards the center of the other planet, right? So if your torque is 0, what's true about angular momentum? Yes. Because torque equals 0, L initial equals L final. So for elliptical orbits, you could use conservation of angular momentum. And if you could figure out the angular momentum at one point in the orbit, we should know the angular momentum at any point in the orbit. Got it? And so now let's think about this. Where is the satellite going to be moving fastest? Close to the planet or far from the planet? Close. It's falling down. It's almost at the bottom. It's at max speed. It goes up to max height. And in orbits, we don't use terms like max height. We often use the terms perigee and apogee. And you can look those up and study this and do angular momentum if you want. Cool. A famous phrase historically, I should mention this since it's, I don't know, kind of interesting. The angular momentum relates to a cross product. Does anybody know a geometrical interpretation of a cross product? It's the area of the parallelogram created by these two vectors. And so what we say is equal areas over equal time, because time plays into this. There's a speed in here, right? So you'll sometimes see these pictures where they'll split the orbit up into these triangles of equal area. And obviously, as the triangles get longer, they get skinnier so that each triangle will have the same amount of area. I don't know if I drew that very well, but if you look on the internet, you'll sometimes hear equal areas and equal times. A physicist would say angular momentum is conserved. So it's really cool. You can read a book. I'm done on that. All right. Okay. How's everybody feeling so far? Good? Yeah, no questions?
I have a question. That is, if for instance, in the case of the two asteroids, just putting it.
This one here, let me get back to my screen here that you're talking about.
It has to do with.
You're talking about this one, we had this and it
Yeah.
explodes, okay?
So when, okay, in the case of a universe where there is no external forces, that in which only those two objects are the ones that exist, will they ever be able to separate from each other, or will they always come back?
In the universe, in reality?
Oh no, like in a universe where there's nothing else, it's completely empty, and those are the only two objects. Will they always end up colliding since they're on the?
Well, remember, it depends on their initial speeds and it depends on what explosive charge you put in there. So I guess what I'm saying is you'd have to have three objects. Or well, actually you'd have two objects, the initial one and an explosive, right? Or a spring, or however you want to think about it, right? Depending on how much energy you use to explode it outwards. Let me pull a different version on this. Let's say we have our universe, the one we actually exist in, and everything's condensed down to one little point, like at the Big Bang, and then it blows up. You have enough energy when you blow it up, it's going to keep going forever and spreading out forever. Some say the world will end in fire. Some say it'll end in ice. Isn't that some weird Robert Frost poem? And we're getting out there today. But right, that's the classic poems, right? So, right, if you have enough energy, you explode outwards, and it's the heat death of the universe as it ever expands and cools off. Whereas if you don't have enough energy, it's going to explode and come back together and just keep. But I'm, yeah, whatever. Is that cool?
Yeah, kind of.
It's like more questions, right?
Well, still have the same one, which is to what extent can the forces apply, or can two objects apply forces on each other?
Yeah, that's a good question.
They're the only ones that exist in an empty universe. Shouldn't they?
1 over r squared doesn't technically ever really go to 0, but in practical terms, it does. Here, let me ask you another question. Here, just come up here for a second. I want you to stand with your back right here, facing me. Okay, stand right there. No, this side of the line. Okay, that's good. All right, so now, let's say we're standing here. I'm going to walk halfway towards you and stop. About right there. Now I'm going to go another half the distance. Will I ever reach it if I'm only going half the distance?
No.
Well, Zeno would argue that that's the idea of a limit in calculus class. We know in practice, if I get close enough, we're going to be like COVID-orific up here. All right, let's give him a round of applause. Good job, good job. So in practice, you would say no, but in theory, you would say no, you're never actually finishing the distance. But in practice, we know that yes, you do meet up. So that's the concept of a limit in calculus class. So I feel like that sort of applies here. You're saying, wait, the force never really goes to 0, but 1 over r squared, what do we know about that function in math class? The limit is 1 over r squared goes to infinity.
Therefore, more or less.
Goes to 0. Now, 1 over r doesn't converge, right? So if you know this from calc class, this will come up in physics 163, where we talk about line charges, infinite lines of charges. The electric field never goes to 0 because it falls off as 1 over r. So if you had an infinite line of masses, you would be right. If you had an infinite line, but that's because as you go farther away, there's still infinitely more of them, and there's always enough to pull you back. Got it?
Yeah.
But so with the point mass, 1 over r squared doesn't converge, so that, yeah, good enough?
Yeah. It's good.
Yeah, okay. Yeah, we could go all day on this stuff. So I tell you what I would like to do is let's just take our break now, come back and maybe do 3 more problems to practice this and call this chapter done. Sound good? All right, let's take our break. It's a good time. I have 12:03 on my clock. says on there.
I think so. Yeah.
Jules, do you know when our final is? Oh, could you look it up on robjorstad.com if you get a chance?
For sure.
Yeah, it's the same day as my count.
I think it's 2 weeks from today.
Yeah.
Yeah, so whatever 2 weeks from today is. So we're gonna finish chapter 13 this hour. Next class, we're gonna start chapter 14. Lab, we're gonna finish up any codes you got this week. And then next week, we're gonna finish chapter 14 on Monday, hopefully. Next Wednesday is the last day of class, and we'll just try and do review or loose ends or any questions you have. If somebody's clever and can figure out Costco and I buy, maybe somebody can buy pizza for us or something. We can talk about that in lab or something. So
do we have lab next Thursday?
no lab next Thursday. Wednesday is the official last day of class. Yeah, so no lab. So yeah, because some people might have finals starting next Thursday. Or wait, not next Thursday. Next Thursday. No,
Next
Next
This
Thursday.
upcoming Thursday, and the one after that, there's no lab,
right, because
Next
finals could
Wednesday.
start.
is Wednesday,
Really?
and then the Monday after that is
Something like
final.
Yeah, for our class. Yep.
I got all of my finals on that day.
That's great. Get it done.
Yeah.
All right.
Nice.
Now, up till now, we've been doing a lot of problems with numbers and especially problems with angles with numbers. I want to show you another style. And I want to look at problem 13.14, everybody. So this is another one just to really be a master of. And Jules can tell you later, this looks exactly like Physics 163. The problems that we're doing in this chapter are the best preparation for 163, which a lot of people think is the hardest course they're going to take in all of their college careers. So you gotta know this stuff. So if you need a little extra juice, another extra reason to study, the reason is this will help you in the next class, which is really freaking hard. Okay. Let's say we have two masses here, big M. Draw this off to the side. And then right in the center, there's some mass over here, and I'm going to stretch this out just so I have room. Let's say this is a little mass M. And I'm going to label it up here so I have space. I spent a lot of time in the solutions on this problem with a couple of different styles. So if you don't like the way I'm writing this up, you should refer to those solutions as well. Also, make these pictures big. Okay, you want to have a big picture. We need a lot of space to label on this one. Okay. Okay. Now we're told that the distance between them is not A, but 2A. So in particular, notice the distance right here would be A above, and this is A below, because I believe it says that exactly in the problem. Yeah, so you might be saying, what if it's not centered? It does indicate that it's centered. And then we're going to say this distance over here, X. Those are all center to center distances. Okay. All right. The point of this is to learn how to deal with algebra and angles. Okay. Algebra and angles, because in the real world, sometimes it's efficient to model a problem algebraically when it has angles. So there's going to be two gravitational forces acting on this little mass. All right. One of them is going to be directed this direction. We could call these, maybe we could give them numbers. And usually I would say this is like problem number 1. Let's say this is mass number 2. And over here, let's say this is mass 3. Okay. So mass 2, whoops, oh, that looks like 2m. I don't want it to be 2m. How about I make one like that? Sorry about that. So mass 1 has capital M, mass 2 has capital M, mass 3 has little m. Now we know that there's going to be a force of 1 on 3. Similarly, there's going to be a force of 2 on 3. Which one of these should be bigger? Force 2 on 3 or force 1 on 3? Which one should be bigger?
They're both the same.
Same, because they have the same size mass, they're the same distance away. So now, this is G M1 M3 divided by radius 1 to 3. And now we got to choose. Are we going to do a vector? Let's do a force vector here, okay? So if I want to do the force vector, how do you want to do this? Do you want to do this as a squared or a cubed? Cubed? So if we cube the denominator, I need to multiply by what on top? Not quite.
The magnitude.
Negative the radius vector. You agree? Because it's got to be attractive. Help me out then. What is radius 1, 2, 3? I'm going towards 3. And let's just assume we have a normal XY coordinates for once. So by that, I mean, this is the x-axis and this is the y-axis. Let's not make up something fancy here.
The square root of a square. root
Nope.
of-
I want the vector. So I want it in Cartesian form. You're jumping ahead. You're jumping ahead. I just want the vector from 1 to 3.
X I hat minus
X in the I hat.
minus A J.
Yeah. Got it? And then what were you saying?
Well, that's equal to the square root of a squared. plus
Yeah,
b
so
squared.
you were talking about R1 to 3, not R1 to 3. Right? That's what's annoying about this. So he was saying this is the square root of. Now, you could say square root of. I'm going to get a little spicy on you.
To the 1/2.
Yeah, just because in my experience,
It's easier.
it's easier to write it this way because then when you cube it, you just change it from 1/2 to
3/2.
3/2. Got it? And so notice out of all this, we're going to get a negative sign. That's from right there. We get a G. We get a M. We get a big M. That's the wrong order. Then we're going to have this. And then we're going to have and just so that this minus sign pops, I'm going to redraw it in red. Everybody cool with that? How much SOHCAHTOA did I have to use? None. Isn't that sweet? Now, let's be fair. Could you do this problem with SOHCAHTOA? Absolutely. Let's take a second to do that really quick with SOHCAHTOA and see the difference. It would be G M M over x squared plus a squared to the 1/2 squared. That's the force magnitude. And I can put an angle in here. It would be negative cosine theta in the I hat. I'm going to pause. Do you agree it would have a negative I hat with the cosine and a positive j hat with the sine of this vector? Take a second to agree with that or verify that. Is everybody cool with that? Okay. Robert, you good with that too? Or you're, okay, yeah, okay. Well, now, how do I get cosine and sine? Well, I could draw a picture here. This side's x, this side's a, this is theta, this is x squared plus a squared to the 1/2. Notice cosine theta would be x and this would be like that, agreed? So, and if you plug in all that crap, you're ending up getting a negative x. We got the negative x this way. You'd have a positive a, we got a positive a. Either method works. Over time, I think you may find that you like this one more. Exception. If things are on a box grid and if everything's either up or down or left or right, man, if things only have one component, this way is super slow. Right? So if things are all on the x-axis, there's no reason to do all this. Well, I should take that back. Almost always this method is preferable. Let me just say it like that. In the real world, almost always this method pays off. Sometimes even in 1D, like problem 13.19. Yeah, you just got to trust me. I know what I'm talking about. This is a good technique to learn. I think it's less complicated. Is that enough said? So now, just in terms of space, I want to erase this term here because we've got the answer. And then I want to work out force 2 on 3. Is that okay? This is written up in the solutions if you want it. I did it that way too. So I just need space. All right. This technique of doing these problems with algebra is crucial for physics 163. If you get used to it, it's not that horrible. If you don't get used to it, it is horrible all semester long. Force 2 on 3. I'm going to get a G. I'm going to get an M2. I'm going to get an M3. Just following the pattern now that we've got it. Because we use the cube, we use the full vector instead of squared and half. All right. And then to make this minus sign pop, I'm going to color it some other color than red. All right. Notice the procedure. If I want to use this, I immediately need to figure out R2 to 3 vector. And if you get in this habit of writing this, then figure out the vector, then plug it in, it works every time. So somebody new, somebody tell me R2 to 3, the vector in Cartesian form.
Wouldn't it just be the reverse of R1 to 3, so negative x and positive x?
No,
It will still be x.
take a look. We're going from 2
Positive
to,
x, positive x.
so it flips just half of it. And that's what I wanted to point out. It doesn't flip the whole thing. And that's, once you catch that, you're golden. We're still going x in the I hat. We still go positive x, but we go positive a this time, or positive j hat. You agree? So now, what is R2 to 3 distance going to be? Same thing. So the distance is the same. The only thing that flips is the j hat, right? I'll get out of the way in just a second. Going to put that negative sign out front just so it matches up here. So again, this minus sign is right here now. And what was it? X to the I hat plus j hat. which component drops out? The j hat. Do you agree they both have a minus sign? They both have the same prefactor. This one's going to have x inside and x inside. It's got negative a, positive a. Let's look at the picture. Does that make sense?
Symmetric about.
Symmetry. So this is the next level that we have not really talked about. We could have cheated. I could have looked at this and said, dude, and this is a good technique that you should use if you can use it. You should say, look, I can tell the force net on 3 is equal to 2 times F 1 on 3 in the X. Meaning I get the entire force vector, clip off the X component only, and double it. Do you agree with that? And isn't that faster than doing this whole procedure twice? And so many problems in physics have symmetry. And we're going to work on this more in Physics 163, not so much in this class. But this gives us a way to kind of think it through. We know the net force should be this direction and twice as big as one X component. Right? You could do the parallelogram trick. Make the parallelogram when you're adding 2 vectors. So we could see that this is F net on 3. By symmetry is that. Now to be, just so we have this all on one board, I'm going to write up the final answer. Give me a sec. I'll get out of the way, I promise. I'm just going to use this one. It's negative 2 GMM over x squared plus a squared to the 3/2. And then I got to remember it's a vector. So I got to use that I hat times x in the I hat. By using symmetry, we simplify the amount of math to do. Can you see that all right, Michael? Okay. And it's in the answer key too, if you need it, or you can state it. Just want it on one board for some. All right. Any questions about that? Let's read the question, see what we're supposed to do. Ah! Whoops. Which part did I just do? I just did part B. Do you agree? So I forgot to do part A. Let's go back and do part A really quick. It's something important on part A we should talk about. So I apologize. This was all part B. Let me go over here and start over. Sorry about that. We got to do part A. Just going to redraw. This picture doesn't have to be quite as large. I've actually done most of the work already anyway, so. The x-axis, the y-axis. We told that this distance is A. This distance is A. This distance was X. And then I think we already figured out that this distance here was x squared plus a squared to the 1/2. Is that right? And I believe that was this distance right here as well. So we've got all the distances involved. I want you to learn this one trick. Oh, and we numbered them, didn't we? This was mass 1. This was mass 2. This was mass 3 over here. Okay. highly likely a question like this might appear on your test where I give you 3 masses and see if you can get the potential energy. Now, you probably know how to do this already, but let's revisit this just in case. I have a standard trick for this, for making sure, it's just a note-keeping trick. Okay? The potential energy is associated with each pair of masses. So the way I keep track of them is I keep track of my pairs like this. First, I start with anything that's paired up with 1, and I start at the lowest number. So U1 plus U2. Are there any others that I could pair up with mass 1? 1 with 3, and then I'm done. Then I keep going. Now I go to the next lowest number at start, U2. Now 2 has already been paired up with 1, so I don't want to redo that. Are there any others that haven't been paired? 3. And if you do this pattern, you'll never miss a term. Even if I put 4 or 5 or 6 masses, you always do all of the lowest numbered masses, then all of the second lowest numbers that didn't get hit, et cetera, et cetera, et cetera. If you're into combinatorics, we can talk about how many terms you should see. If you know Pascal's triangle, it's in there as well, right? So anyways, enough of that. I want to talk about it. I got to stop myself. You want to talk about that, talk to me after class. So let's do this. U12 is going to be negative G M M. What's the distance between 1 and 2?
2A.
That's 2A. Then whoops. I'm going to add the next term. I'm going to keep track of that negative. U13 should be. Wait a minute. What did I screw up in U12? I screwed something up.
Oh, the massive.
Do you agree it's not big M and little m for 1 and 2?
2.
I screwed up. It's not 2M, it's M squared, big M squared. Sorry about that. Everybody agree? Sorry about that. Now that's looking good. I have the right masses, the right distance, and I got the minus sign. Check. Moving on. 1, 3. That one's going to have a G, M, big M. Distance between is and then finally, I think it's pretty much the same. Sorry about that, it's a little sloppy. There's the potential energy. Got it? So on a test question, I love to ask you a force question and an energy equation question. That way I can see if you remember the squareds and the minus signs, or the not squareds and the not minus signs, etc. You know what I'm saying? So, right, you could totally expect a 3-mass system on your final exam. I got 3 masses on some weird ass grid, and you got to calculate the force and the potential energy and crank it out. And I would love to do it with either complicated sets of numbers with powers of 10, like scientific notation to see if you know how to use your calculator, or algebraically to see if you know how to deal with no numbers. Got it? I think that's pretty straightforward, but you got to practice it a couple more times, so that's what the homework's for. All right. I want to go back to part C over here. That was part A. Oh, now so part B was here. That part was A. And now I've just got this force here. I'm going to rewrite that over here and then shift over to part C, okay? I'm just getting that term over here. Okay. Okay. So now, our goal is to find the maximum force. And let's look at this in a couple of ways. What happens to the force if x equals 0?
Oh, worse zero.
Why? What is it?
The denominator goes zero.
Not the denominator, the numerator.
Or the numerator,
Yeah, yeah, okay, you meant the numerator. This term in the denominator goes to 0, but the denominator is a cubed, right? Does that make sense? If x goes to 0, you're sitting right here. What direction are the forces? Up and down, and they balance because the j hats drop out. Agreed? Now, let's take this to the other extreme. What if x is crazy freaking big? If x is really big, let's say you're way over here, what's going to happen to the size of each of these forces? If you get farther and farther away, what happens to the purple arrow and the red arrow? They get small. So if you're right at the center, the force is 0. If you're really far away, the force is 0. Everywhere else, the force is something. Agreed? There should be a maximum where the porridge is just right. Okay? How could I find the maximum? Give me multiple ways. Give me one method for finding the maximum. Any method in the entire universe.
Second derivative test.
Okay, you could do derivatives. You could do calculus. What's another way? And that's the way we're going to do it in a minute.
Graphic.
Plot it. Do you agree those are the two most obvious ways to find a maximum? And so in the real world, if you wanted to find a maximum and you were getting paid to do it, what should you do? Both. So you can check it and make sure you're right. Maybe even make a simulation and code it and show people. You see what I'm saying? So you should do both methods. That's where I was getting at. Don't trust what anybody can make a mistake on one method, but the odds of you screwing up both are pretty low. So you do both and you check your work.
What if you screw both?
If you screw up both, well, you can find a new job.
Yeah.
Yeah, right. All right, so let's practice the calculus way. And at first, people get scared by these, but the trick is just kind of settle in and cruise through it, right? Don't try to do too much in your head. Don't try to do too much in one step. It looks ugly at first. Just be patient with yourself. Let the paper do the work, and you're done in no time. It's not that hard, okay? Now, you said do some derivatives. I need more than that. Tell me what I take the derivative with respect to, what I take the derivative of, what do I do with it? Give me a step list of what I need to do.
So you will need the derivative with respect to x, right?
We're going to take the derivative with respect to x of what? Of the force, and then do what with it?
Set n equal to 0.
Then do what?
Then plug it back in and solve for x.
So then we solve for x. We call that x critical, right? Then you could do the second derivative test. Now, I believe we already discussed this and we know that there's going to be a maximum because we know it's 0 here, it's 0 there. So we don't need to do a second derivative test for this particular case. But if you weren't sure, you could do it. All right. Well, now you're going to get this on occasion. Just trust me on this. The move is, since we're going to take a derivative and set it equal to 0, the first step is usually get rid of any constants. Now think about this. I'm going to show you this. I'm going to take the derivative. I'm just going to pop the constants out. -2g, mass is a constant, mass is a constant. I hat is a constant. And then I just need the derivative of this. Everything that's left. These are all the constants. By doing that, when we set it equal to 0, we could just ignore the minus sign, the I hat, the 2's, the g's, the n's, all that crap. The other thing that I'm going to do is nobody wants to use that stupid quotient rule. Everybody has the product rule memorized, right? F prime G, G prime F, you don't have to think about minus signs. So convert this exponent to a negative, so you're doing a product rule, and you don't have to think about minus signs, right? Let's just do this. So what I'm going to do is I'm going to say x times x squared plus a squared to the -3/2, like that. And when you do this, the rest of the problem does itself. It's just boring. You could use Wolfram Alpha if you were on the real world. But what I'm saying here is this stuff can never equal 0. When you have two things multiplied together, right? If we have A, and then all of this is B, A times B equals 0, either A equals 0 or B equals 0. Since A cannot equal 0, B must equal 0. Good? So then usually I don't even write the constants in practice. I just go straight to this. And I would just delete this, delete all this, and save myself some headache. And then you're like, okay, it's much more manageable now. It's a normal calculus problem. Got it? All right. So let's just work through at least the first step of the chain rule to see if you guys have a clue. Okay. What do we do here? I'm going to do derivative of the first times the second plus the first times the derivative of the second. Give me something. What's the first part when I take the derivative here? Let's see how your brain works.
Break down the power.
Bring down the -3/2, the power.
That's subtract 1 from the power.
Okay, so then I rewrite this junk to the negative what?
5/2.
-5/2. Okay, then what? Take the derivative of what's inside. Without any power. Well, this part times the derivative of what's inside. Yeah, you got it? You remember all that crap? If not, I wrote this up in very gory detail in the solutions. Basically, this, you take the first term times the derivative of the second. The derivative of the second, the power comes down, you get this to -1, then you take the derivative of that junk. When you take the derivative of that junk, you basically get 2x. So now, this particular derivative happens a lot in physics classes. Right, Jules? You remember this all the time in that next class? So, right, you want to get this, it's not that this one particular problem is better than any other. It's just, it happens a lot where you get these 3/2 and these derivatives. So just be good at this, okay? So now I'm just going to clean this up. You get used to it, right? This term drops out because it's 1 times that. I got a 2 here that cleans up that 2. I've got an x here, so I'll make it an x squared. That takes care of this now. And then you can rewrite this thing in this form. We bring the power back down so that it looks normal. And all that was equal to 0. From here, there's lots of ways to proceed. All we've done is taken the derivative. We have not found the critical value yet. But you could solve this, set it equal to 0, and you're off to the races. Do you agree? All right, so in this case, what do we get out of all this junk? Did I work it out? Well, I tell you what, I'll let you finish that one. You could use the solutions to finish it out. We're running out of space here. Okay, did anybody look up the solution real quick? I'm gonna look it up just so you have it in the video. Or if you're faster than me, if you got it up. What problem was this? Whoops, not 163.
13.14.
13.14, okay. Control F, 13.14. Where was that? So it looks like out of all that, I got A over root 2. So the answer to this ends up being X critical equals A over root 2. And I believe there's a plus or minus on here. Yep.
So it makes a 45-degree angle.
Not quite. So that was the question. Okay, so let's go look at it. Oops. So the idea is if this side is A and if this side is A over root 2. So is it going to be? Yeah, it will be a little bit longer, right? Because A over root, well, let's see. So let's try and draw it to scale here. So A over root 2, isn't that 0.7?
That's gonna be shorter.
A, yeah, so it's going to be something. If this is A, probably be about right there. Now, here's the issue, right? When you're really close, the forces have more J hat, which cancels out, but the horizontal components are bigger because you're closer. And so that's the trade-off, right? It's just kind of a weird balancing act. So what? Is that good?
Yeah.
So it's not a 45 degree. Yeah. And then how could you check this? Graphic, right? And if you didn't want to use Excel and know what you're doing, you would plug it into, what do most students end up doing? Like Desmos or something like that? Or a graphing calculator, or I just do it in Excel and learn how to use Excel, but whatever, yeah. So maybe this is you probably don't want to do this, but this is another one that you should probably do the plots. This is like the first week of Physics 163, right? So if you get used to dealing with this one and knowing how to plot it, you'll be faster. And in 163, those first couple of weeks, you'll have an edge, I hope. Good enough? There's all kinds of extra cool stuff about the binomial expansion. Maybe I'll come back to that if we have time. Make sure you do 13.21. I don't have time to do it in class, but that's a great example of that's another, like, that's the last of the classic exam level type questions. That one looks pretty good to me because you see how it's just a big mess of different parameters and you have to keep them all straight and solve it algebraically. Okay. Oh, there it is. There's 13.17 gives you the geosynchronous orbit if you're into that. 13.20, let's talk about that one really quick. On page 123. So I'll erase really quick and find some space. Actually, we've got a little bit of space over there. Does it? It looks awful. Turns out it's a piece of cake. And that's what I wanted to show you. Doesn't 13.20 look horrible? What's that?
Three-dimensional, right?
It's three-dimensional. I'm only going here because this is the space I have to work with. You know, it's like erasing the board takes much longer than it really should. Still haven't heard back on my work. No idea what's going on. We've got these 5 point masses, and I want to label them the same way. 1, 2, 3, 4, 5. 1, 2, 3, 4, and this is 5 over here. And to be clear, there's a coordinate system. So this is supposed to be in 3D. This is not like, so, yeah, I can't draw very well in 3D. Hopefully the book looks a little bit more neat than this. What direction is the net force on 5? What direction is the net force on 5?
Negative y.
Negative whatever direction I called that. In the problem, was this the x direction here?
Yeah.
Was this x? And this is the y direction?
Yeah.
And then up would be z?
Yes.
Okay. So in this case, this is not that hard. It looks horrible though. The trick is this. First, figure out the force of 1 on 5. So we would get R1 to 5. Well, I go negative s in the I hat. Oh wait, negative s over 2, but that's half the side of the square. Negative s over 2 in the k hat. I know I'm out of order here. And then I go some distance y in the j hat. Jules, am I still on the screen?
Yeah,
Just barely? Okay. So, and you guys can see, okay. Well, now, can't you just get R1 to 5? Magnitude is the square root of s over 2 squared plus s over 2 squared plus y squared. And you can figure all that out. Notice this is not going to be s squared. You agree? This is not s squared because that's going to be s squared over 4 plus s squared over 4. Now you get force of 1 to 5. And it's going to be some ugly vector with an I hat, a j hat, and a k hat, right? How do you get the net force on 5? Trim off, keep the j hat, multiply by 4. Done. Not as bad as you thought, right? So that's the joy of symmetry, simplifying our work. Now I know I just sketched this one out here, but I know I wrote this up in detail in the solution. So like this is kind of the level of skill we definitely need in Physics 163. Might be slight overkill. Most of the, I'm going to put a planar problem on your final. I'm not doing 3D on the final. You got that? That said, I think there's a lot that can be learned. So like if you have time, this is the one extra problem you might consider doing. Got it? You can learn a lot that way. And in 163, we're going to do that. All right. We're on to fun topics here. We've got some fun topics. Take a look at 124. I've completely glossed over this. Page 124. At the top of the page, it says reduced mass. I need to erase sometime, so I guess this is it. I'm just erasing on Zoom. I'll be right there. You're a physics major. You need to know this. You're a physics major. You need to understand reduced mass. So I'm going to mention it. It's also interesting because it relates to the tides on this particular planet that we all live on. Well, it's kind of interesting. Not to mention, it's good practice for circular motion. So I'm just going to say it like this. Up until now, we've been talking about the central mass is always so big, it remains motionless, right? And you just showed me a code where that was not quite true, right? But what was that? We're going to talk about reduced mass. And I'll try and use the same picture. It turns out there's a really cool mathematical trick you can do. So let's say we have object 2 right here, and object 1 is smaller over here. But for some reason, the center of mass is between the two, right? The center of mass is not at the center of 2, because 2 is not infinitely large. Turns out the center of mass of the Earth-Moon system is not at the center either. It's like 2/3 of the way out. It's like 2,400 miles from the Earth's center. So this actually is a very good model. Now, object 2 is going to orbit that center of mass, right? Think about it. There's a conservation law we could talk about. Now, whatever. We kind of did already. Right? Something like that. Okay. So these two objects are going to orbit that center of mass. Now, in this case, right, you can think about the forces. They're always going to be acting towards that center, right? As they go, the center of mass is always going to be directly between them on the line of action for both forces, agreed? And so it makes sense to use the center of mass as a pivot point when we're visualizing this. All right. In this case, we're going to get some force equations. Now, the force depends on their center to center distance, right? We'll call that, what did I call that? D? Center to center distance I called R. Sorry about that. In this problem, just trying to keep the notation. But now the circular motion, you could say it's v squared over r, or you could call it r omega squared. Now, in this point, what I'm trying to clarify here is this is the radius of 1. It's orbiting the center of mass. So its centripetal acceleration depends on the radius to the center of mass. Right? You could also say it's equal to, but it turns out I think it's actually easier to visualize this one if we use the omega notation. Is everybody okay with that? Now, what is radius 1? Well, we could do a center of mass problem to show that, right? And in this case, did I work that out? I think I did. Oh, I think I called this X in the picture in the problem. Sorry about that. And I worked this out just using the center of mass formula. And so if you want, we could go through that. But again, I'm more interested in just the result here. Okay, so I'll clarify what matters out of this problem in the end. But notice when you put this up into this force equation, right? I plug this radius into here. I set this equal. We see that the mass drops out. Notice we get this weird term. Okay. And it turns out, if we work this all around, we get a result here. I want to write it like this. Oh, yeah. Maybe I'll write it like this. this term, if I don't cancel this out, let's not cancel this out. Sorry about that. When you look at this thing in the equation, do you agree that this entire term has units of kilograms? And so what happens here is if you have two objects and one of them is not infinitely massive, they're both orbiting the center of mass, mathematically, it works out that the little mass could actually be reduced by this factor big M over the total mass. Now think, big M is slightly smaller than big M plus little m. So this is slightly smaller than little m. That's why it's a reduced mass. This is probably, you may have heard of this in your chemistry classes when they say, well, you got to use the reduced mass of the electron when talking about the Bohr model and blah, blah, blah. If not, maybe you'll hear it there. Hey, this is not on the test, but if you ever hear this term reduced mass, it comes from this effect of when something's orbiting the center of mass of a two-mass system, we get this mathematical artifact showing up, which can then, you can redo this problem and just saying, well, it's a standard circular motion problem if you use the reduced mass. Whoops, mr omega squared. Sorry. All right, that's enough on that. So if you want to learn more about that, great, there's a problem there, you can figure this out. The note at the bottom, the similar thing happens when the electron orbits the hydrogen nucleus. And you can actually observe the effects of this reduced mass in the hydrogen spectrum. So if you're wondering, I know this was keeping you up at night why the spectral lines were shifted according to this reduced mass. I know you were losing sleep. Whatever. I'm gonna do one more thing, and then I'll get you out of here. Not on the test, not on the test. I'm gonna go back and do it because I can't help myself. I want to look at 13.12 really quick. You do not need to take notes on this. If you want to just leave because you're so sick of this class, I'm not offended. Okay, if you want to just leave because you're tired, that doesn't offend me either. I'm erasing. 13.12. It will not be on the test, but it's interesting to me. You can just sit there and relax, put your stuff away, and I promise we'll work this out really quick. If you're a physics major, you should definitely see this. So these last two little bits are like the only time I ever throw the physicists a bone. I got to do it sometime. The rest of this class is pretty applicable to most students. Let's get caught up here. Still erasing. Still erasing. Good enough. Okay, get the right screen. Okay, let's check this out. Not on the test. Say we have a mass here. The radius of this thing is r, so I'll just say the diameter is 2r. With some object here that's some distance h above. You know the gravitational energy is G m over r plus h, negative, right? So that's the potential energy when we're sitting up there. Now in this case, m could be the mass of the Earth, and r could equal the radius of the Earth. And I think that's how I phrased it in this problem. So now I'm going to show you something that's a standard physics trick. And again, I cannot stress this enough. You do not need to write any of this down. The solutions are there. This is not going to be on the test. I just find it extremely interesting and valuable to physicists. Okay. I'm going to rewrite this way. Actually, I'm going to redo it this way first. What I'm going to do is I'm going to try to make this a little bit prettier by first making it uglier. All I've done is I factored out this radius. By doing this, think about this. If we are near Earth's surface, h is small. So h is going to be a small number compared to the radius. That allows me to rewrite this in this way. I'm rewriting this by bringing this to the numerator, raising it to the -1, and I'm renaming this small parameter delta. Delta means something small. Now, maybe you know the binomial expansion. Maybe you don't. But 1 plus or minus delta to some power here, n, is approximately equal to, if you do the binomial expansion or Taylor series expansion, it's 1. And then I guess the next one would be, let's see, does it have to be plus? I think it would be plus. Something like that. You could look this up in a book. This is called the binomial expansion, or it's related to the Taylor series expansion of this. We're going to call it the binomial expansion because this is a binomial, right? There's two terms to some power. Well, check this out. That means this is approximately equal to negative GM over R times the quantity, let's see, 1 plus, in this case, n is -1 times delta plus delta squared plus delta cubed, etc., etc. Now keep in mind, if delta is small, delta squared is hella small, delta cubed is hella small. So these terms are approximately equal to 0 compared to this. This is an approximation. We keep the first order term, okay? So now notice what we get out of this. Using the binomial approximation, u is approximately equal to GM over R times H over R minus GM over R. Now, I did a little math here. Look, I put the positive term first, so I put the negative there. Delta was H over R. So this term right here was delta, right? Is everybody okay with that? Well, now, what do we get here? I've got an M times G M over R squared times H minus a constant, right? Does anybody remember what this is? That's little g. Do you see we get mgh plus a constant? And then we could just change our height to set this constant to 0. We're good to go. One of these days I'm going to be smart enough to stop doing that. Because now I got to dig in there and find those stupid markers every time. But I'm just so excited. I just wanted to show you that this equation is approximately equal to this as long as h is much, much less than the radius. This equation is only true if delta is small, which means h has to be near Earth's surface. That's why we always have been using MGH near Earth's surface. All right, get out of here. Oh my goodness. I wonder how many markers are in that pit at this point.